In today's session of operating system, we'll be dealing with the next set of CPU scheduling algorithms. We have already done with the FCFS and SGF. Now we'll move on to the next algorithm, which is nothing but shortest remaining time first, which is a primitive version of SJF. So these are all the process which are present, and these are your arrival times and the burst times of that particular process. So starting with the arrival time of 0, you just check out what is the process that is present. So P1 is present with an arrival time 0. So you will not be executing for the total burst time. Make sure that you are executing only for 1 millisecond. So since I am executing it for 1 millisecond, the burst time reduces to 6. Now at 1 arrival time, you just check how many processes are in the ready queue. You have P1 already and P2 is added. So among these two processes, you just check the remaining time. What is the remaining time here? 6, and this requires 5. So in this, which process will be scheduled for execution? You go for scheduling P2, and that too for only 1 millisecond, and reduce the burst time. This becomes 4. Now, when you are at P3, now you are at 2 milliseconds. You got 3 processes which are in the ready queue, and check their burst times. Whichever has the least, that will be allotted the CPU. So P3, and you just execute it for 1 millisecond, and this reduces to 2. Now when you are at your third millisecond, you even have the fourth process which is coming into picture, and the time of it is 1. When compared to the remaining 3 processes, this has least burst time, so you allot the CPU to P4 and make it sure that it is executed for 1 millisecond, and the burst time of it reduces to 0. So it means that it has completed its execution and removed from the ready queue. Now when you are at 4th millisecond, check what are the next process that is added into the ready queue. So P5 is also added into the ready queue, and the burst time of it is 2. But when you cross check here 6422, you have two processes with the same burst time. So in case of a tie, we'll go for using FCFS, meaning that whichever arrived at first, that will be executed. So among these two, the arrival time is P3. So P3 you continue executing for 1 millisecond. So after you execute for 1 millisecond, the burst time of it remaining time reduces to 1, and you got a new process which is P6 with the same burst time. Now you have P3 and P6 with the same burst time, but say use the same FCFS. So according to FCFS, you continue with P3 for 1 more millisecond. So if I continue it for 1 more millisecond, this particular process has completed its execution. So it becomes 0. This is also done with the execution. Now, at 6th millisecond, if you check, you don't have any other process that is entering into the ready queue. They are all fixed. So now P1, P2, P5, P6 are available. So you go for the normal SGF algorithm. So among all these things, check which one has least burst time. So you have P6. So P6 will be allotted to the CPU for 1 millisecond, and the burst time of it will become 0, and this is stopped its execution. And among after that, you have again your P5, the next least burst time, which is to be given 2 milliseconds. You don't go for stopping it. Now it becomes your same preemptive. So you execute it for 2 milliseconds, the burst time of it becomes 0. So it becomes 9 because you are doing it for 2 milliseconds. Now you are left out with P1 and P2. Among this, you go for giving P2 for 4 milliseconds, which becomes 13, and this also is done with the execution. Now I'm left out with only P1, where the burst time of it is 6, where put together it is 19. So this is your Gantt chart for the available arrival times. Now we try to fill up the completion time or the finishing time. When did P1 complete? At 19 milliseconds, P2 at 13. Seeing the Gantt chart, you need to try it. P3 at 6 milliseconds, P4 at 4 milliseconds. When I go for P5, it is at 9 milliseconds. When you go for P6, it is at 7 milliseconds. And you know how to calculate your turnaround time. Turnaround time is nothing but your completion time minus your arrival time, whereas this is nothing but your turnaround time minus your burst time. And when you go for your non-preemptive, I told you very clearly waiting time and response time would be same. But coming to the preemptive version of it, the value will not be same. So this is nothing but your first response minus your arrival time. Now when I go for P1, when did P1 get the first response at 0 8 second? So this is 0. Now, when P2 got the first response at 1, though P2 is repeated for the next time, P2 you are again getting, this is, you got the first response for P2 at 1. Similarly, P3, though it is repeated 3 times here, you just concentrate when the first CPU was given. Here, the first CPU was given at 2 milliseconds. Similarly, for P4, the first CPU was given at 3 milliseconds. And P5, the first CPU was given at 7th millisecond. And when you go for P6, the first CPU was allotted to it at 6th milliseconds. Now, minus, you know the arrival time of those particular process, minus the arrival time, you get your response time. After you calculate your turnaround time and waiting time, we need to calculate the average turnaround time and the waiting time of this particular process. So when you go for this SRTF, what are the advantages? The process are executed faster because it is preemptive. You're stopping one process if P1 is executing, and you are getting the next process P2 of less. You're stopping this P1 and continuing with P2. Whereas the problem with this SRTF is context switching is more. You need to go for switching from one process to other process. And like the SJF, you may not be all times available that the large process. It leads to starvation if the process has more amount of burst time. And it is impossible in practical situation. It is impossible to implement it in interactive systems where the CPU time is not known to you. Now we move on to the next scheduling algorithm, which we call it as priority scheduling algorithm. Till now we have seen FCFS, where it was purely based on your arrival times, and we have even seen SJF, where it was based on your burst time. Now here, coming to priority scheduling algorithm, it purely depends upon the priority of the process. Depending on the operation done by the process, we assign an integer value to each and every process. And based on the priority given, we start scheduling. And when you have two types of priorities, one is a static priority, other is a dynamic priority, where if for P1, if I assign a priority as 1, throughout the program, the priority of it will be same. So it is static. Sometimes in interactive systems, the priority of a process can be changed. In priority scheduling, we have two types of it as of your SJF. One is your preemptive, the other is your non-preemptive. Coming to non-preemptive priority scheduling, before we move on to this, when you see the priorities that are being given to a process, a smaller integer number indicates the highest priority. So this is the smallest number indicates that it has the highest priority, and this is nothing but your lowest priority. Smaller integer value becomes your highest priority, the corresponding arrival times and the burst times, and this calculations are also done here. Now, when we start with always the Gantt chart will start with the arrival time 0. So at arrival time 0, this is non-preemptive. So once you allot a CPU, use that CPU till the execution of its burst time. So P1 is being given. What is the amount of burst time here? 3. So CPU will be withheld with P1 for 3 milliseconds. Now at 3 milliseconds, you identify what are all the processes that are present in the ready queue. So P1 is already done, right? So P2 has come and P3 has come. So when you check P2 and P3, now you have two processes which are present in the ready queue. Which one you will be selecting based on the priority? As I said, the larger integer value has lower priority and this has higher priority. So we go for scheduling P3. Now P3 should be scheduled for how much amount of time? It has to be scheduled for 4 milliseconds. So you already executed it for 3 milliseconds. So this will be executed for 7 milliseconds. So after that, this is done with the execution part of it. Now, you are at 7th millisecond. Identify the process which are present according to the arrival time. You got P4 into your queue. You even got your P5. You even got your P6. You even got your P7. So all the processes are now there. So when now you have to check the priority of this particular process. So when you go for checking the priority of the process, since all of them are available, among this is 6, 5, 7, 4, 10. Now we'll go for P6. What is the burst time that is allotted to P6? It is nothing but 4, which is leads to 11. 7 plus 4. Now I'm already done with P6. Now you check the remaining all other process. So this is done. Now 4 is done. Priority of 4 is done. This is done, and you already executed this. Now you are left out with 6, 5, 7, and 10. Among 6, 5, and 7, we'll go for P4. P4. What is the corresponding burst time of your P4? 2. So this would be 13. So you've also already finished executing your P4 also. Left out is 6, 7, and 10. You go for now giving it to P2. P2 burst time is 5. So P2, 5. 5 would be 18. 13 plus 5, 18. So this is also done. P2 is also done with its execution. Now you are left out with P5 and P7. P7, P5 priority is 7 and burst time is 9. So you will be just going for P5 with 9, which is nothing but 27. So P5 is also done with its execution. Now you are left out with P7, the last priority, and the burst time here is 10. So this is nothing but P7 with a burst time of 37. So these are all your completion times. You can just cross check it here. After you finish doing all these executions, so P1 completion time. So here I've already mentioned the completion times, and you know how to calculate your turnaround time, waiting time, and the response time. And make sure when you are calculating this, what is the waiting time and the response time of each and every process. And we need to even calculate the average waiting time, average turnaround time, and average response time of a process. Now we move on to the next scheduling algorithm, which is nothing but priority scheduling preemptive. So in this, we'll start with first process of arrival time 0 will be started, but afterwards, if you have any other process, so this is the next process which you are selecting, and this is the before process. So if the next process which you want to select, the priority of it is greater than the priority of your before process, and you go for selecting that particular process. Otherwise you continue executing your previous process, and if the priority of the two process are same, then finally we go for using FCFS based on their arrival times. Now we'll see an example of priority scheduling preemptive algorithm. So we'll start to fill up the Gantt chart here. So when you go for this Gantt chart, we'll start with an arrival time 0. So here in the Gantt chart, if it is 0, what is the process that has arrived at 0, 1? So this are your process IDs P1. So P1 is allocated to this particular process for how much amount of time? 1 millisecond. And the burst time is also 1. So it has done with its execution. So you need not bother about P1 further. Now you are at 1 millisecond. So just check the arrival times. 1 millisecond, which process has entered into the ready queue? P2. And it is only process in the ready queue. So directly assign it to the CPU. So P2, but not for the total burst time. You assign it only for 1 millisecond. So I'll assign it for millisecond, and this reduces to 6. Now you are at 2 milliseconds. Check how many processes are entered. Now you have P2 and P3 both in the ready queue. Among these two, which one you select, you check the priority. Which has least priority, that would be of highest priority. Least integer value indicates highest priority. So you assign this P3. For how many milliseconds? Only 1 milliseconds. And this reduces to 2. Now you are at third millisecond. Sorry, this would be 2 and this value would be 3. Now you got your P4. Now P2, P3 and P4, check the priority 6, 3, 5. So chance will be again given to your P3 for 1 more millisecond, which would be 4 now. And this reduces to 1. Now you are at 4th millisecond, and which is a process which is present in your ready queue? You have P5 at 4th millisecond. Check 3, 5, 4. Again chance will be given to P3. So P3 can execute for 1 more millisecond, which is nothing but 5. And the burst time of it would become 0, meaning that it has completed its execution. Now at 5th millisecond, you just cross check that you even got your P6 also. Now you are with 2, 4, 5, 6. The corresponding priorities are 6, 5, 4 and 10. So 6, 5, 4, 10, which is minimum value here P5. So P5, what is the burst time given here? 5. And you just even check the arrival time of the next process. It is at 15th. So you need not check for 6, 7, 8, 9, 10. So you can allot the CPU for total amount of time. So I'll go for allotting the process to after this. What is the next process? I can give P5 and allot it for the total burst time. What is my total burst time here? 5. So if I allot it for the total burst time, it would be 10. So I don't have any other new process entering at 10th arrival, 10 milliseconds, right? Now, whatever are present. So what is done here, P5 is also been executed. Now you're left with 2, 4 and 6. Among 2, 4 and 6, you again have your next process, which is of 5. So you go for executing P4. And when is the next process arriving at 15th millisecond? So you have 5 milliseconds, right? So out of 6, you execute it for 5 milliseconds. So when I execute it for 5 milliseconds, you left out with only 1 and this will become 15. Now at 15, you have a new process entering, which is nothing but P7 and the priority of it would be 9. So you have 9, 10, you have 5 and you have 6. Now, when you see these values 6, 5, 10 and 9, you will be again giving a chance only to your P4 processor because it is of highest priority. So P4 and how many seconds it requires? Only 1 millisecond. So I'll just make it as 0 and this would be 16. So my P4 is also done with my execution. You're left out with 2, 6 and 7. Now when you see, you don't, after 15, you don't have any other process which is entering into your ready queue. So it normally acts as your normal priority queue where you totally give the CPU to that particular process. So among 2, I'm repeating it once again, 2, 6 and 7 will allot the process to P2 first. So when I allot it to P2, allot to take the total CPU time. It is 6. So it would be 22. Now P2 will also be done. Now you'll go for the next one, which is nothing but P6 and P7. Now I'll just go for P7 and allot for the total amount of time. So you're at 22. Your P7 requires 8 burst time. 22 plus 8 would be 30. So P7 completes at 30 and this is also done. And the last priority process is nothing but your P6. P6, just cross check the burst time, which is nothing but 15. 13 plus 15 would be 45. So these are your completion time of your process. So accordingly, we'll update the completion time and you know how to calculate your turnaround time and the waiting time and the average waiting time, turnaround time of each and every process. Coming to the advantages of this priority, whether it is preemptive or non-preemptive test, it is very easy because you're only checking the priority and allowing a process to execute. And coming to the disadvantage of this particular priority scheduling here, the lowest priority process, if the system crashes, the lowest priority process will not get a chance to execute at all. And it can lead to starvation because you are only allowing the higher priority process to execute it. So lower priority process will be under starvation, meaning that the process will be waiting in indefinite amount of time for the CPU. So a process will go on waiting for the CPU, which will be only given to the higher priority process. So lower priority process will be in a longer waiting state. So that is nothing but a starvation. So to overcome the problem of starvation, we go for a technique known as aging technique. So what we do in aging technique is, if you have a lower priority process, we just change the priority of the process for every second. Assume for every 5 milliseconds. If the priority is 15, I'll deduct it with 1. So next 5 milliseconds. So priority has now become 14. Next 5 milliseconds, 14 minus 1 is equal to 13. So as the time increases, the priority of the process will be going on reducing. So if my integer value gets reduced, the priority of the process will go on increasing. So this is the aging technique. Now we'll see the next scheduling algorithms in the next class.